we are doing CDM for conjugate direction method first, then we'll get to conjugate gradient method. Okay. So the cost function which I had, which was half of x transpose Ax minus b transpose x. If I want to visualize this cost function, of course there is the b transpose x, which is simply a linear part. Let's have a look at the more interesting part, which is x transpose Ax, which is the quadratic part, right? So let's see. Okay. And to help us visualize things as quickly and easily as possible, I'm going to make life very simple. I'm going to assume A is a diagonal matrix. Okay. Assume A is diagonal. Okay. Fine. So this is my very simple, straightforward matrix. Okay. And let's look at the conjugacy condition. What is the conjugacy condition? Pi transpose Pj is equal to 0, I not equal to j. Okay. This is a diagonal matrix. Can you immediately guess one set of p's such that this is satisfied? 1 0 and 0 1, right? So supposing I have 1 0, this matrix A, and 0 1, you can see that this is going to be equal to 0, right? Also, the other way of seeing it is, what are the eigenvectors of this matrix? 1 0 0 1, because it's a diagonal matrix. Eigenvalues are 2 and 5, right? So automatically I can see that 1 0 0 1, these are the eigenvectors of this situation. Okay. Now in this case, if I plot x transpose Ax, what is the kind of geometric figure that I get? We did this a couple of classes ago. If I plot x transpose Ax in the x1 x2 plane, what do I get? I get an ellipse, right? Oops. I get an ellipse. Now if I look at the conjugate direction method, what is it saying? The first direction in which I must go is which direction? The first conjugate direction, 1 0, for example. So let's call this P0 and let's call this direction P1. Okay. So 1 0. So let us say I started from here, some random starting point. What is the solution to this point? Assuming, well, I don't need to assume, this is a convex function. The red dot is the solution. It's the global minima to this problem. What is my first move going to be? Along the x1 direction. The second move is going to be along which direction? x2 direction. So if I want to get to the red dot and the first move is only along the x direction, x1 direction, where do I move? I move horizontally and I move where? Hit the x2 axis, right? So the first step is going to be actually boom here, right? The second step is going to be only along the x2 direction. There is no choice. Where do I go? Straight down to the solution, right? So you notice that my emphasis here was to look at the underlying geometry, which was the conjugate directions, go along the conjugate direction. I didn't see whether, how perpendicular I am to the contours of the cost function, which I did in the gradient descent method, right? If I were doing gradient descent method, what would I do? I would do something like this, right? Steepest descent means go in the direction that is along the negative gradient, but I didn't do that. So my motivation is cover the ground in each of the directions so that I reach here. So you can see that in 2 steps I am at the solution. And you can also see that if you got lucky with a starting point, supposing I started along the x1 axis or along the x2 axis, what will happen? One shot I reach there, because there is now no other ground to be covered in the next step, right? The other case, which is quite simple to understand, is A is non-diagonal. Okay. So if A is not diagonal, We also did this with, yes, question. Is there a clever way to choose an initial value? Can someone answer that question? What is the cleverest way of choosing an initial value? Hmm. Why is highest necessary? Okay, so if I were to, like in this example, if I chose my point to be along x1 or x2, I'm saving one step. Right? So if I get somehow, my luck or my skill has to be in figuring out these directions and going along. Ultimately, it may not matter so much, it's order, I mean there are only n steps, so I'll get there. Okay, when A is not diagonal, how do we visualize this? We have seen it's a rotated ellipse, right? But that was, what was the rotation with respect to? With respect to the eigenvectors, right? But now I want to visualize in terms of what? The p's. I'm given the conjugate directions. I want to work with conjugate directions. Eigenvectors happen to be one candidate. Okay. So this expression over here, I can insert identity here and here in a clever way, right? So identity I can write as, so let me take my P matrix as P0, P1 all the way up to Pn minus 1. This is my P matrix. I got all my conjugate directions over there. Okay. What would be a nice way of writing identity? I can write in terms of P and P transpose because it's invertible, right? So if I insert it in this way, I can write P transpose, or I can write it as P inverse, the same thing. Okay. Actually, it's not the same thing. They are not orthogonal. So if I give me P, let me write it as P inverse. That is identity. Okay. So it's not transpose. So what will this become? This will become, so A P inverse X. Can you guess now what I should do on the, for the identity on the other side? There's going to be a transpose operation over there. I can also write identity as P transpose inverse. That is also a legit way of writing identity, right? This guy I can insert over here. So what am I going to get? P transpose inverse P transpose X. Okay. Now this guy, okay, if I call this guy to be Y, okay, let me do the following. I'm going to move this over here. This is also correct, right? And there's a transpose missing over here. So this term over here, what is it? If Y is P inverse X, what is Y transpose? X transpose P inverse transpose. So this becomes Y transpose. Okay. Now what we are left with is this matrix P transpose AP, where P is, you know what, the matrix over here. Is there anything special about this matrix? Is it necessary? These are not eigenvectors, these are only conjugate vectors. So is it necessary for it to be to have lambda? It's diagonal. Why is it diagonal? Because if you look at P transpose, what is P transpose? P0 like this, P1 transpose like this, right? This is my P transpose, this is my A, and this is my P0 this way, P1 this way up to Pn minus 1, right? So when I take this multiplied by A multiplied by any other column, I'm going to get 0, right? P0 transpose A P2, what is it? 0. The only term that is going to survive is P0 transpose A P0, that's 1 1. Similarly, P1 transpose A P1, that's the only term that is going to survive. So this is actually going to be a diagonal matrix. So this is a little bit more clever because I am not insisting on eigenvectors, right? I just need A conjugacy and I am getting this to be, therefore, this is Y transpose AY. Sorry, not AY, dy. Right, this entire expression simplified over here, Y transpose A transpose, sorry, P transpose AP became dy. What is this looking like now? This looks like case 1, right? In the Y coordinate axis, what is it? What shape is it in the Y coordinate axis? An ellipse, right? So if I were to plot this along Y1, Y2, I'm going to get ellipses, right? And we already have Y is equal to P inverse X, implies that X is equal to P times Y. Okay. So in the Y coordinate frame, the easiest way to solve the problem is to, so supposing now I am solving this problem in the Y coordinate axis, this is exactly like case 1, right? First do this, then do this, right? So a step along the Y1 axis is what step in the X axis, in the X space? P into, so let's take Y1 is going to be given by 1, 0, 0, 0, right? This is my Y1. If I stick this into here, what am I going to get X as? Which column of P will get extracted when I multiply by Y1? Only the first column. First column is what? P0, right? So if I am walking along the Y1 axis in the X1, X2, let's call this P0, need not be perpendicular, P1, right? So the first move over here is actually going to be along this direction. So every walk along the coordinate axis in the Y space is a walk along the conjugate directions in the X space. The next step that I walk is going to be Y2, which is 0, 1, 0, 0, 0. That is in the X space P1 and P2, Pn, right? So every step in the Y axis along the coordinate axis is a step along the conjugate directions, right? So is that clear? This is a very important, this is the geometrical intuition of the conjugate direction method, right? Going from non-diagonal to diagonal is trivial. A simple linear algebra, inserted identity, we split it, we saw that what's happening, keeping track of X space and Y space, right? So now this gives you the motivation for, you know, whoever came up with this method, probably, right? They saw this geometry and said, hey, why bother with descent directions? If I know the solution is here, the best way I could, a clever way in which I could do it is walk along each step. You notice I am never retracing my steps. If I walk 5 centimeters along x1 axis, I never revisit the x1 axis ever again. Whereas in the gradient descent method, it had a zigzag kind of a trajectory. In that, I am revisiting each direction multiple times. And possibly at every iteration, I am walking along each of the coordinate axes, right? But here, it's very efficient in that way that just walk along the axis once, right? So at least that's my understanding of how what the motivation would have been.